Hey, hi everyone. Good evening. Yeah, I hope I am audible and visible. I'm just setting things up. Give me 1 minute till also other folks join in. So we'll wait for a couple of minutes. Okay. So yeah, let's start. I think we have a good amount of people. So today, I want to discuss a genre of problems known as the scheduling problems. Okay, where we'll be looking at different types of schedules. So we'll be trying to schedule, say, meetings. We'll be trying to schedule interviews, slots, and schedule jobs in an OS, and therefore solve problems. Okay. So let's go to the first problem, and in that we will in the three problems I want to discuss today. In this, we'll learn around 4 5 different types of concepts. So, and these will be very helpful in terms of like long questions in interviews. So long questions are generally often involve like good amount of reading, going through the question, and then trying to come up with a data structure, how to solve it, right? So if you understand the pattern, if you understand, okay, what the problem is trying to tell, it becomes easier to solve it, right? So let's go into that. I'll share my screen first, and then let's talk. So one of you can confirm if the screen is visible, if the audio is clear, then we'll start. Just waiting for a response. Awesome. Okay, so yeah, so let's start. So let's look at the first problem that I wanted to discuss today. We'll call it let me just search for it. So yeah, courses, discuss this problem. Took it out, but I forgot. Yeah, so say there are uh, uh, k courses that are given to you. Okay, so there is a, say, a variable called so you are given k courses that you have to schedule, and you are given a prerequisites kind of a thing, saying that okay, once you have taken course A, only then you can take course B. Okay, so like if you have taken say C++ or Java in semester 1, then only you can take operating system object oriented programming concepts in semester 2, like this. Okay, so let's say you have something like this. So you have, say, num courses kind of a variable, right? And num courses essentially it tells that there are 0 to num courses minus 1 courses are there. Okay, and there are prerequisites given to you. So prerequisites, as I said, it means that whether you are able to uh, take a course, or when you are able to take a course, right? So say if I give you 1 3 2 3, and your num courses is, say, 4. So what are the courses? What are the courses we have? So the courses we have are 0 1 2 3. Courses we have are 0 to num courses minus 1, right? So 0 1 2 3. Out of them, what is dependent on what? So 1 3 is dependent on 1, so you do 1, then only you can do 3. And 3 is also dependent on 2, so you do 2, then you can do 3. And 0 is separate, so 0 is not dependent on anyone. 0 you can do independently, course 0, right? So this is the problem. The question is, you have to return, or you have to tell whether you can so return a boolean which tells whether you can complete all the courses or not, or whether you can take all courses or not. Okay, so an example when you cannot take courses, and an example can be something like this. So say 2 depends on 1, and say 3 depends on 2, and say 5 depends on 3, right? And 7 again depends on 3, and sorry, 3 depends on 5. Okay, so let's then you have say 7 depends on 2. Let me actually change this. So say 1 depends on 2 depends on 1, 3 depends on 2, and so 1 2 3 we have. So say uh, 5 depends on 3, okay. 7 depends on 5, and say 3 depends on 2 depends on 7, right? So in this case, because 2 is dependent on 1 and 7, right? 2 is dependent on 7 is dependent on 2. Yeah, so let's change this actually. I want to make 7 is dependent on 2. Yeah, so because you can see that 2 is dependent on two things, 7 and 1, and then 7 in turn is dependent on something like 5. 5 is dependent on 3, and 3 is in turn dependent on 2, right? So in this case, you will never be able to complete all the courses, because there is something like a cyclic kind of a dependency, right? So how would you solve the problem, or how will you uh, determine the order? Say, first of all, let's discuss about how will you return true or false given the problem statement. Okay, so this is the question. Now let's discuss. Anyone can think of a possible data structure we can use, or a logic we can use to solve the problem. No answers yet. So any hunch on what kind of data structure we can use in this kind of a scenario? If you are just given the prerequisite map, okay, we have one possible approach. Okay, so Kajal has come up with a possible approach. Anyone else? How do you represent the data so that you can solve the problem? Anyone else other than Kajal? Any data structure you can think of? No one? Okay, so Kajal, so what kind of an approach would you have and how will you implement the data structure you have in mind? You can unmute and go ahead if you want to share the approach.
Sir, we can map the sticks and I don't know actually. But बस आपने cycle बोला तो I thought graph हो सकता है.
Okay, so graph seems to be a good approach, but will not directly. So graphs seem daunting as a data structure because there is a lot of information in graphs that we think of capturing. We can just think the data structure as, say, we can just have a map. Okay, we can just have a map where we have the prerequisites associated with us in some form or the other, right? So ideally what we can have essentially is a data structure like this. Let's write it down. So we'll not have for implementing graphs there are multiple ways. So we use something like uh, we use something like what do we call it, adjacency list, adjacency matrix and stuff like that. So we'll not go into those parts. We'll just discuss how we can store it and how we can process it, right? So let's say we have a list kind of thing and we are just map kind of thing and we are just adding the prerequisites. So we can have something like 1 as the key, and what are the things that have prerequisite for 1. So 2 is a prerequisite, sorry, so which are dependent on 1, right? So this is a course, so the key is the course and the value are the dependents, right? So 2 is dependent on 1, then 3 is dependent on 2, then 5 is dependent on 3, 7 is dependent on 5, and 2 is dependent on 7, right? So this can be a map, and then we can see which of the elements are completely independent. Okay, so the first step is to see which elements are completely independent, right? So here say num courses was given to you as 8. So that means courses are there 0, 1, 2, 3, 4, 5, 6, 7, right? So can you tell what can anyone tell which of the courses are completely independent? So okay, so 0, 4, 6 are independent that we can see. There is also other yes, 1 is also independent. So yeah, Vikas has a good intuition there. So 1 is definitely independent. So see, apart from 0, 4, 6, 1 is also independent, right? You don't need 1, you don't need anything, any prerequisite for 1. So these are independent courses. So we have 0, 1, 4 and 6. right? Other than that, everything else are dependent. So 2, 3, 5, 7, all are dependents, right? Perfect. So we know that we can complete these things independently. Okay, we are done. Now, from here, I want to spawn. Okay, if I have done 0, what other things I can do? Can I do anything else? No, right? Nothing is dependent on 0. Same goes for 4 and 6. Nothing is dependent on 4 and 6. So 1 on 1, 2 is dependent. So say I have some data structure, and you have to tell me after we discuss what kind of data structure you want to use here. So say for 1, I know that, okay, I need 2, right? Then once I have done 2, right? So I have 2. Now I have only thing in this data structure. So once I do 2, what else can I do? Okay, first of all, can I complete 2 or not? I cannot complete 2, right? Because I have 7. I need to complete 7 to complete 2, right? So because I need 7 to complete 2, and from here then I cannot complete anything. So from 1, with 1, I can only say that there is a possibility to do 2 if I have completed 1, right? There is a possibility to do 2 if I have completed 1. But can I do 2 at this moment? No, right? Because I need 7 to be completed. But could I have completed 7 now? No, obviously, because 0, 4, 6 or 1, nobody allowed me to complete 7, right? Nobody directly allowed me to complete 7. So for me, what I'll do essentially is I will not, in this case, I'll not be able to complete the problem, complete the this thing, the courses, right? Why will I not be able to complete? So if I do 1, can I do 7 at this point? I cannot do 7 at this point also, because for 7 I need to do 5, for 5 I need to do 3, for 3 I need to do 2, and for 2 to be done I again need to do 7, right? So it's a cyclical kind of thing. So at this point I cannot add any of the other elements in this data structure, right? So let's look at the other case. Let's look at this case. So initially, which were independent for me in 0, 1, 2, 3? Can anyone tell what were the independent ones in 0, 1, 2, 3? Yeah, so which one will be independent? Let's see. Okay, 0, 1 and 2. Yes, 0, 1 and 2 will be independent, right? All these things are independent in this case, right? So say I do the course 0, right? The moment I do the course 0, can I do anything else? No, I can't do anything else. So I do 1. When I do 1, can I do anything else? No, I cannot do anything else. So I complete 1. Then I do 2. Now can I do anything else? Yes, because 1 and 2 is done. In that data structure that I have not named yet, I insert 3. Right? Because 1 and 2 were done. So I insert 3. Then I check. Then I come to this data structure. I take it out. I see, okay, 3 can be done because, and nothing else is dependent on 3, and we are complete. All the courses are done. So here you return true. In this case, you were not able to proceed, right? In this case, you were not able to proceed. So you return false. So can anyone think and tell what this data structure will be? Can anyone take a hint? Obviously, in this case, there is only one element, but it can increase continuously, right? Okay, Rudnan has an answer. Anyone else? So what kind of data structure can this be? Perfect. Kajal also has an answer. So we can use a queue for this kind of a data structure, right? So this can be a queue. Okay. Now the next question, how do we know that 3 can now be done since we have processed 1 and 2? So what kind of counts we need to maintain and how do we need to change the count so that I know that 3 can be done once 1 and 2 are done? Can anyone think of how I can store the count? What counts I need to store? and how I can update them such that I know when 3 is available for processing. That means I have done 1 and 2. Can anyone think and tell what we need to maintain and how we need to update it? So basically, when can I say that 3 can now be done? So we have a map here that we have discussed. We have a queue here. What else do you need? Okay, no one has an answer yet, so I'll go forward with the answer. So say when I was creating the map, right? When I was creating this map in this case would have been something like 1 to 2, 1 to 3, 2 to 3, right? This would have been the map. So in this case, when I was creating the map, if I could have a another map, right? Another map saying how many things are 3 dependent on, right? So whenever I get a value, I increase in this map. So 3 first 1, then 3, then 2 also maps to 3. So how many? So 1, it gets incremented by 1, 2, right? So if I can have a map like this, which basically tells how many courses is this course dependent on. Okay, how many courses is this course dependent on? And every time I find a course that is a prerequisite for this, I reduce this count. I start to reduce this count, right? So I will enter that element only in the queue when this count becomes what? So what will I need the count to be when I can enter it in the queue? That means that course can be done. Exactly. So I want that count to be 0. I want that this count to be 0, right? Because I incremented it that many times to create the map, right? And this you can call something like, say, incoming edges. So this is the first graph term I am using, but not necessarily it's a graph term. You can just think of what are the courses, number of courses that this current course depends on, right? So this is the incoming edges, and the moment incoming edges become 0, I update the queue. Right? I add that element in the queue, right? So let's take another example. Let's take, say, another example. Let's try to dry run this, our logic, whether it runs or not. Okay, so let me keep the example like this. Say there's a course 0, and or say yeah, there's a course 0, say, which has how can I explain? Yeah, so say it has 3, it has 6, 6 has, say, 1, then or let me just put this like this. So I have 0 here, okay, in the middle, and then say 2 courses are prerequisites for 0, say 3 and 7, then there is 6, then there is say 6 is dependent on say 1, and 1 also is prerequisite for 4 and say 2, and then 7 is for this, and 5 is for this 1. Okay, 5 is a prerequisite for 1. So let's now calculate the hash map, right? The first hash map that we need. So the prerequisites hash map basically. Okay, so we can have we will have something like this. So if 0 is the key, what is 0 prerequisite to? 0 is prerequisite to 6. Okay, so this is the course, or this is the key, this is the prerequisite. Okay, then what is the prerequisite for say 7? Or what are the courses which are prerequisite to 7? So 1 and 0, right? 1 is a prerequisite to again 6, right? 5 is a prerequisite to 1. Let me know if I miss anything. 1 is a prerequisite to also 4. 1 is a prerequisite to 2, right? 1 2 3 4 5 6 7 8 1 2 3 4 5 6 7. I have missed 1. Can anyone tell which one I missed? I think I missed 3, right? So 3 will be for 6. 0 is a prerequisite. Yeah, we have mentioned that in the first, but for 3 I haven't. So 3 is a prerequisite to 0. This looks correct, right? Everyone on the same page? So 7 points to 1 and 0, 5 points to yeah, so this looks correct, right? So this basically, these are the edges, nothing else, edges of the graph. Again, I don't want to use graph terminologies, it is not that complex. Okay, it's a very, very simple algorithm. Now I'll also now count the inbound. So when I created the map, I know that 6, how many inbound edges 6 has? 6 has 2 inbound edges. One is this one is this one that comes from 1, right? So whenever I insert in the map, I can create this. So how many inbound edges does 0 have? I can start from 0 only. So let's start. 0 has 1 inbound edge, so I call it inbound. 0 has 1 inbound edge. Then actually I don't need to call them inbound edges. I can, yeah, I will need this. I'll need this. Sorry, inbound edges. Yeah, 0 has 1. Then I have 0 has 1. Then 1 will have 1 again. No, 1 has more inbound edges, right? 1 has 2 inbound edges. 2 has 1 inbound edge. 3 has 0 inbound edges. 4 has how many? 4 has 1. 5 has 0. 6 has 1. And 7 has 0. Have I made it correctly? Yeah. So 5, 7 and 3 have 0. Right? Okay, 6 has 2. Yeah, 6 has 2. Perfect. 6 has 2 inbound edges. So when you create this, basically you can figure out, right? So what did I say? Which of the elements I'll move to the queue? So these are my 2 data structures I have created. This is 1 and this is 1, right? So initially, which of the elements will I move to the queue? So this is another correction I needed to make. So yes, I will move to the queue only those courses which has 0 inbound. What does 0 inbound mean? That means there are no prerequisites. We can do them independently, right? So I have 3 0, I have 5 0, and I have 7 0. So I move them into the queue. 3 5 7. Okay, I moved it to the queue. Now I'll check. Now I'll pop element from the queue. So I'll pop from the front. I pop out 3. What are dependent on 3? 0 is dependent on 3, right? I can see from this graph. I'll change the color so that everyone understands the working of this algorithm. And this is a very, very important algorithm. Okay, pay attention. So the moment I find 3, I know that 0 is dependent on 3. So what I'll do, I'll say that, okay, one of the courses that 0 was dependent on has been done, has been processed, right? So 0 now has only one dependency left. Cool, done. 3 is now popped from the queue. Now I have 5. What is 5 dependent? 5 prerequisite for? 5 is prerequisite for 1. So I update. I say that, okay, I have taken a course that 1 was prerequisite for. So I update this. I remove 5. I have 7. What are the courses 7 was prerequisite for? 1 and 0. So this I decrement, this I decrement. The moment I decremented 0, I'll add it to the queue. The moment I decremented 1, I will add it to the queue. 7 is processed. Everyone understood why I decremented and why I added to the queue? Any questions? Till now. So this is, yeah, anyone has a question, tell me. So we are just, what we are doing, we are saying, okay, this queue needs this many prerequisites. If I am complete with the prerequisites, I know that these elements have become independent, so I can now pull them, right? I can now process them. Okay, now I go here. What are the elements? 6, 0 is a prerequisite for 6. So I check 6. How many prerequisites? 2 prerequisites are there. Okay, so I make it 1. 0 is now popped. I come to 1. Tricky part, there are 3 prerequisites. So I update. For 6, I make it 0. When it becomes 0, I add it to the queue. Then I see 4, it becomes 0. I add it to the queue. Then I go to 2, it becomes 0. I add it to the queue. Everyone still fine? Now I come to this element. 6. I see, is there 6 is a prerequisite for anything? No. 6. So I just remove from the queue. 4. Is 4 a prerequisite for anything? No. I'm done. 2. Is 2 a prerequisite for anything? No. I'm done. So if I complete, when I'm done, I can also keep a count. If I complete all the possible values, right, 0 to 7, that is 8, right, or my maximum queue size, not queue size. So if I can complete processing all the elements from 0 to n minus 1, num courses minus 1, I say that I return true, otherwise I return false. Okay, so this is the algorithm. So we have a map. So we have a prerequisite kind of a map. I have a queue to process it, and I have a inbound edge, a hash map again, inbound map. Awesome. So Vikas has a very good question. How do we take elements in the queue at first? So in the beginning, Vikas, we are only taking the elements which had 0 initially in the inbound edges. So we took 3, we took 5, and we took 7. The ones with the black mark, right? Because they had 0 prerequisites. That means they can be done independently. So initially in the queue, I pulled 3, 5, and 7. Okay. And then I started processing elements in the queue. So now my question, can anyone tell what this algorithm is called? This algorithm has 2 beautiful names, one in the context of trees, one in the context of graphs. Can anyone tell what the algorithm is called? So you can unmute and guess also. So there are no penalty points for wrong answers. No one? What is the tree name? Like, what is this approach using a queue? What kind of thing is this called in the context of trees? So this is not by any means a tree, right? As Kajal mentioned initially, this looks like a graph. I didn't want to use the word graph. It is a hash map at the end of the day. But if you had to think of it like a tree where each element had at max 2 dependents, right, a binary tree, what would you call this approach using a queue? No one? Yes, so Rohit has a good answer. So it's called BFS. So it's a level order traversal. It's a breadth first search that we are doing. We are looking at the breadth. We are looking at all the possible elements and then solving it. So this is a level order traversal or a breadth first search, whatever you want to call it in the context of trees. In the context of graphs, what is this algorithm called? A hint will be we are trying to find an order. So if you see here, we are also figuring out the order in which the courses are being taken. We are also figuring out the order in which the courses are being taken. Can anyone tell what this type of ordering in a graph is called? Or what is the algorithm name? No, this is not a shortest path algorithm, Rohit. So we are not finding the shortest path if you see. We are nowhere trying to find a path, whether a path exists. We are trying to find if we can cover all the elements. If we can cover all the elements, whether like in what order is the elements getting covered, right? We are not, no, this is not in order traversal. That is done. The traversal part is done. This is a level order traversal. So we are not going into the traversal part anymore. So that's a very tree-ish name, right? In the context of graphs, what is this ordering called? When we think about orders, what type of algorithms do we think of? If you have to order an array, what type of algorithm do you call it? If you have to order the elements in an array or a list, what type of algorithm do you call those algorithms? Exactly, right. So they are called sorting algorithms, right? Any type of ordering algorithm is a sorting algorithm. So what sorting is this in the context of graphs? This is by no means a heap sort or a merge sort algorithm. So heap sort, merge sort are very, very different things. We are not using a heap here. We are not using any merging here. We are just taking elements from a graph and we are trying to sort them. No one? Okay, that's very disappointing. I thought CS folks are can answer it. So this is known as a topological sorting algorithm. Okay. Very complex. It is taught very, very badly in colleges. I'm not talking about any particular college. It's taught badly in every college, wherever it is taught. If it or it is not taught altogether because graphs come at the end of the semester when the semester is ending, like right before the exams. And if you teach them, if you teach that, then you have to take it in the exam, and mostly people don't pay attention at that point of time. What is being taught, right? So this topic is not taught in most of the colleges properly. This is a very, very, very important concept in graphs. Okay, so this algorithm is known as the topological sorting algorithm, where we use two maps and a queue. We can use a list and a queue. Multiple ways are there of solving this problem. So this algorithm is called, and I will write actually in red letters, red letters. So this is known as topological sorting. I want all of you to understand this algorithm. If you have not paid attention here, go home, look at the recording, look at YouTube, but make sure you know this algorithm. Okay. If you go into an interview and tell I don't know graphs and topological sorting, that's fine. But if you can solve this problem logically, so I did not discuss graphs here, right? Apart from this inbound map, I did not talk about graphs. I tried to solve it very logically. So this problem is actually very logical. Okay, this is also known as by other name by the scientist who created this algorithm, right? So it has another name to it. So it's known as Kahn's algorithm. but in the algorithm world, it is known as topological sorting only. Okay, perfect. So any questions in this algorithm? Anyone? Any questions? Everyone understood the use case? Everyone understood the process? I'm happy to explain again if there are questions. So I'll explain the question once again. Okay, there is a request. So the question is, there are a set of courses. Okay, so you are given a set of you are given a number num courses, which means the set of courses is 0 to n minus 1. So 0, 1, 2, 3 essentially. Okay, so these are the set of courses, and you are given a set of prerequisites like this. So that means three. If you have to take course number 3, you have to do course number 1 first. If you have to do course number 3, you have to do course number 2 first. Okay, given this kind of prerequisites, will you be able to do all the possible courses? This is the question. A true false answer. Okay, so given a set of prerequisites and given a set of courses, will you be able to uh, will you be able to make possible all the possible courses? Okay, so this is what the problem statement is. Make sense? And we solved it by having one map for the prerequisites, this map, the prerequisite map, one map for the inbound counts. That means like how many dependencies I have, how many prerequisites I have for each course. So this and this are basically the reverse kind of maps. So this is the count, this is the values. And we have another thing, a queue that we are using to solve the problem given these two maps. We are only inserting elements in the queue when inbound counts are 0. Right, that means that those courses are available for processing or available for taking. Yeah, okay, everyone on the same page? Cool. So let's move to the second question. So the second question now is again the same parameters hold. So you again have n courses, right, which is 0 to n minus 1, and again there are prerequisites. Now the question is, you can take courses parallelly in a semester as long as their prerequisites are completed in a previous semester. In a previous semester, any previous semester, okay, any earlier semester if it is completed. So you have to find out how many semesters, how many minimum semesters needed to take all the courses. Okay, how many minimum number of semesters needed to take all the courses? Okay, so an output of this can be for 0, 1, 2, 3. There are 4 courses here, right? So you could have said that I want to do it in 4 semesters. How why? First semester I will do 0, second semester I'll do 1, third semester I'll do 2, fourth semester I'll do 3. But you have to find the minimum. So a better way will be first semester you do 0, 1 and 2 because you don't worry about they are all independents. In the second semester you do 3. So answer will be in minimum answer will be 2. You can't do any less than that. Right? Yeah, we are for now assuming all the courses can be taken. So the question can also be like that you cannot take, like maybe you might not be able to take all the courses, then that this problem becomes a subset of the previous problem, superset of the previous problem, right? So you have to make that check for the previous problem, like you have to check that first. But for now let's assume that you can take all the courses. In that case, how will you solve the problem? So you have to find the minimum number of semesters needed to complete all the courses. Can anyone modify the previous algorithm itself and think about a solution? So if I have to take this example, this complex big example, so I'll say that in my first semester, the minimum way I can do it is my first semester I can do 7, 3, 5. Then in the second semester I can do maybe because 7, 3 and 5 are done, so I can do only 0, right? Because 0 is dependent on 3 and 7 only. So I can do 0. Can I do 1? Yes, I can do 1 also because 1 is dependent on 5 and 7. So I can do 1. Can I do anything else? No, I can't do anything else, right? Yeah. So then in semester 3, I do the courses which are dependent on 1, like say 6, 4, 2. So I need 3 semesters to solve the problem. Okay, Rudnaran has an answer that we can just go over the map, the inbound map, and check what is the maximum value. So if I had courses like this, Rudnaran, so 2 has 6 prerequisites. Would your answer be 6? Or what will be the answer in this case? In this case, the answer will be in semester 1, or the optimal answer will be in semester 1. I take 1, 3, 4, 5, 6, 7, and in the next semester I take 2 because I have done all the prerequisites in the previous semester. So I just need 2 semesters to complete, right? So not necessarily will the inbound map will have the answer, but how do I solve it? Can anyone modify the previous algorithm a bit and come up with the answer? Or can you find a pattern how the semesters Okay, Pradosh has an answer. Unique number of inbound values at start. Unique number of inbound values. So in this case, I had 0, 1, 2 as the unique numbers. So you are saying 3. Here, how many unique numbers do I have? I have unique numbers are 0 and 6. 3, 6. Yeah, so 2. Can I refute this? So unique numbers of inbound. Hmm. Not necessarily it will be unique, but yeah, I'll try to find a find a use
So
case, find
if
a
a
test case
map
where it might
contains
be.
values like
Yeah, there is an
for
answer.
0 we have 0 prerequisite, for 1 we have 1 prerequisite, that will be the previous element, then it would not be applicable because we are covering all the previous element. And
Which one are you saying? Can you repeat?
like for 0 to 3,
Mm-hmm.
0 has 0 prerequisite in the inbound.
Okay. These are my courses. And okay, 0 has nothing, and then
1 has 0,
okay.
like for the inbound map,
Yeah. Then
the counts.
okay.
1 has 0 has 0, 1 has 1, 2 has
Okay.
2, 3 has 3. That is the previous courses.
Okay, so if I have to build it, so 0 has 0, so I have nothing to do. 1 has 1, so this, then 2 has 2, this, and 3 has 3.
So when we are traversing, we would push 0, then decrement the count of 1.
Right,
Now we
and 2,
reach
1 and 2 also, 2 also,
yes 2 and 3 also.
not 3,
Then
not
the
3.
3 has also 0, 1 and 2.
Oh, 3 also has 0 and 2. Sorry, yeah, okay.
So when we reach 1, we have already completed that. So
We
we
have
could
done
push
its
it in.
prerequisite, okay.
Then for 2 also.
When we push 1, then we update 2 and we update 3. So then we push 2 and then we do 3. But that
So
validates, yeah.
we are doing all the courses parallelly in the semester and the
We are doing
prerequisites
it
are
in 4
complete.
semesters, right? Not in one semester. So only 0 I did in first semester because it had no prerequisites. Once I completed 0, then only I could do 1 in the second semester. Because
Okay, but we are doing courses parallelly and the
parallelly, but
prerequisite.
the prerequisites has to be completed in the previous semester, na?
Okay.
Yeah. So this part is there, right? Prerequisites are completed in a previous semester. Okay. You can do courses parallelly. So 0 and 1 are not being done parallelly. They are being done serially, right? So only once 0 is done, then only 1 can be done, not parallelly. So this is being done in semester 3 and this is being done in semester 4. So I have not been able to refute Pradosh's this thing claim, but anyone else can come up with a more intuitive answer. Or from the queue processing itself, can you tell how many semesters I need? So what I was essentially looking for as an answer was like whenever you are processing the queue, right? Whenever you start to process the queue, the number of elements that are there in the queue, only those elements can be picked up in that current semester. Okay, let's take an example. So where is my so let's take this example, right? So initially what elements are there in the queue? So initially we have 357, right? If you remember, initially we have 357. So only these three elements can be taken in one semester. Okay, now once we pop 3, what do we add in the queue? We add 0 in the queue, right? No, once we pop 3 we don't add 0. Once we do both 3 and 7, then only we can add 0. So once we pop 3 we can do nothing. Then once we pop 5, can we add anything? No. Now once we add remove pop 7, can we add anything? Yes, we can add 0 and 1. So now these old things are done. Whatever elements are there, this will take a new semester, right? Whatever elements are there, this will take a new semester. Then I check for 0. Once 0 is done, can I do anything? Yes, I can do 6. So I add 6. In that same queue I am adding, right? But I know that only 2 elements were there. So I'll check for only the first 2 elements. Then 1 is there. So when 1 is done, I can add 4 and 2. So now 0 and 1 are done. Now these 3 elements can be done in the third semester, right? So I will just check how many elements are there in the queue at the beginning, right? At the beginning of each level, I will check how many elements are there in the queue, and only for those number of times I'll do a push and pop kind of an operation. And once I have done pop 3 times, again whatever is the size of the queue that is left now, because those elements will have some dependent elements added, right? Whatever is the size of the queue now, those will then be my courses for the next semester. And like this, I can say, okay, how many semesters I need, right? So this problem is very similar to figuring out the number of levels in a tree or the height of the tree. So say using a level order traversal, if you have to find out the height of this tree, right? Using iterative method, using level order traversal, what would you do? You will add it to a queue, right? You will add 1 to a queue first because that is the root. Can you add anything else right now? No. You are adding 1 to the queue, you are done. Now you are going into that. You are checking what is the size of the queue. The size of the queue is 1, right? So you know that at first level, I have only 1. Then you pop 1 and you add its children. So you add 2 and 3. You are done. You cannot add anything else. Now you go here. At this point, you check, okay, what is the size of the queue? You see 2. So you will do it 2 times. You will do pop 2 times. Okay. So you pop 2. When you pop 2, you add 4 and 5. You pop 3. You add a 6 and 7. So your level 2 is done. Now you again take a count. How many elements are there in level 3? There are 4 elements, 4, 5, 6, and 7. So now you pop 4. Is there anything to add? No. You pop 5. Is there anything to add? Nothing. You pop 6. Is there anything to add? No. You pop 7. Yes, there is some things to add. 8 and 9. So at level 4, what are the elements there at level 4? 8 and 9. Right? Then so 2 elements only. So again, you will pop twice. So you pop 8. What will you add? You will add nothing. You pop 9. What will you add? You will add 10. So at level 5, how many elements are there? 1 element. Then at 10, you pop, there is nothing. So you are done. So how many levels are there? You have 5 levels. The same thing I did in the graph, just that I checked for the edges here. Each inbound edge was 1, right? Each value had an inbound edge 1, inbound count 1. So whenever I found the parent, I know that I can push the child, right? Because that inbound count is now decreased to 0. So a level order traversal can be converted to a Khan's algorithm, can be converted to a topological sorting algorithm. Okay, so now Rohit has a very good question. So if 6 had a child, say I had 15, right? So what, again, I'll just explain again in so everyone is on the same page. So let's say the counts again. So initially I add only 1 to the queue. So my level 1 has 1 element, so I will pop only one time. I pop. When I pop, I add the children 2 and 3, right? Then when I come here, I know I have popped once, so now I'll check the size. So I check the size is 2. So I pop 2 times. So when I pop 2, I push 4 and 5. I pop 3, I push 6 and 7. So 2 times pop done. So I now can see the level 3 size. It is 4. You can see the level sizes, right? So this is level 1, this is level 2, this is level 3, this is level 4, and this is level 5. Okay, so now 4 has any children? No, so I have to pop 4 times. 4 has nothing, 5 has nothing, 6 has 15, so I add 15. 7 has 8 and 9, 8 and 9. So what is the size of level 4? 3 elements are there. So I'll pop 3 times. 15 I pop, nothing. 8 I pop, nothing. 9 I pop, I add 10. So what is the size of level 5? 1. Then I again go, okay, I pop 10, there is nothing else. So the tree has 5 levels. Right? Rohit, is this clear? Level order traversal? Okay. So your homework will be to read about a level order traversal if you already haven't read. Right? Level order traversal in a binary tree, it uses a queue to solve the problem. And do learn about topological sorting. Okay. Any questions till now? So I'm not writing the code for topological sorting. Okay. So I can put the code, but again, you can always find the code. You can write the code yourself if you have understood the problem statement, if you have understood how to write it. So I can maybe just add the, see if I have Java code, I can add it essentially. I don't have the code with me at the moment, but you can implement it, right? You can use a hash map, you can use a like 2 hash maps and a queue kind of thing to solve the problem. Okay. So if there are no other questions, let's move to one last problem for the day. So this problem basically tells say we have an array of elements now. Okay. Say we are designing a CPU, a single threaded CPU. Okay. What is the property of a CPU? CPU will schedule jobs, right? So it's a job scheduler kind of a thing. What are jobs? Jobs can have a start time, that is the minimum time when they will start, and how much time they will take. Okay. So say the first job, the time it will start is at least 3, and it will take say 2 units of time. Okay. So like this, there are multiple jobs available to you. Okay. So like this, say there are many jobs. So then you have say there, I will add 3-4 more jobs here. So I will add 3-2 is there, 1-2 is there, 2-4 is there, and say 4-1 is there. Okay. So what does this signify? each job signifies two things. AI is the minimum start time, that it can start only after 3 a.m. or 3 p.m. or 3 seconds. Okay, and this is the amount of time it takes to complete. Okay, so these are the indexes, as you can see. So if the CPU is empty, which job will it pick? If CPU is empty, or if CPU is idle, it's a single thread, right? So only one job it can do at any particular point of time. So if it is idle, it picks job with smallest time needed. Right? If the job is empty, it picks job with, if the CPU is empty, it picks job with smallest time required. Okay, and if there are two jobs with smallest time required, it will basically take the one with the smaller index. Okay, so if there are two jobs with same time required, it will take the one with the smaller index. Okay, so you have to return the order in which the jobs are done. Okay, so you have to return the order in which the jobs are completed. Okay, so Mirza has a very good question. So if the time required for the job is small, but the job has not arrived till then, that means the minimum time, start time is say very high. Say you had something like here. So you have 4 1 kind of thing, right? So at time 0, this job is not available. So you cannot start that. You can only start it after 4 seconds. Even if the time is small, if the job is not, if you have not reached 4 seconds, you cannot start that job. So this is the first criteria. If at this point of time there are multiple jobs available, then between them how you choose is this logic: smallest time required or the index. Okay, so for this one, can anyone tell the answer? Like what will be the answer in how the jobs will get picked? Can anyone think? And yeah, so first, which element first arrived? So which of the index first arrived?
First one.
Yeah, one by one, please. One of you can just tell the index.
First.
Okay, so index 1 arrived first because that is at 1. Perfect. So I think, yeah, multiple people wrote in chat. Cool. So when 1 is added, so how much time it took? So it took from 1 to 3, right? Because 2 units of time it took. By 3, which of the jobs came? 3 2 came and 2 4 came. Which will get scheduled first between these two? 3 2 will get scheduled, right? Because it has lesser amount of time needed. So 0. This is the index. Then how much time it takes? It takes to finish 5. 3 plus 2, right? At 5, which of the jobs are available? This and this. So which one will be picked first?
4 1.
4 1. So 3. I'm just writing the index, right? And finally there is only one left. So this one. So this goes till 6, right? 1 second only. and then because the last one is left, so your answer is this. This is the problem. How will you come up with an approach? It's a very, very interesting problem to solve. And this is a real world problem also. So it's a single thread CPU is what you are trying to do. Yeah, go ahead. Someone is saying something. Did anyone say something? I didn't hear. Okay, nothing. Cool. So yeah, think about it. How will you come up with a solution to this? Anyone can think of what kind of a logic we can have to solve the problem? Seemingly a very simple problem, right? So you have to just
Sir,
know. Yeah,
first thing we can do is sort the whole list by the order of their arrival time.
sort the whole list by the order of the arrival time. Okay.
Now we check the last element, which would have the maximum arrival time.
Okay.
So we would use a while loop. While time, okay, the first time would be initialized to the first element of the list, arrival time of the first element. Like here in case 1,
Okay.
at t equal to 1, we will check while t is less than the arrival time of max element, that is 4. So until the time is 4, we would sort the elements that are arrived in the by the order of their execution time and execute them and increment the time accordingly. And
Then you are
after,
doing sorting multiple number of times, right?
yes,
So that is like a very, very costly operation. So you'll be doing n log n cross n log n operations essentially, right? So one outside sorting, then you are doing sorting inside. So we are not looking at shortest job first, Mirza. So okay, Mirza asked the question that are we looking at shortest job first kind of thing. It is not shortest job first. It is at that point of time out of the jobs which are available. Can you find the shortest job? Anyone? What can be a good logic to solve the problem? First of all, the problem with Rudnaran's the approach was that if you sort them, you lose the indexes, and if you lose the indexes, you can never find the indexes back.
Then we can use list.
Yeah, whatever you use, if you lose the indexes, you are done, right? Because sorting will anyway cause the indexes to be gone. Okay, there is a solution by someone, but I don't know the name of that person. 26 CSEA3. So can you talk about your approach and who are you first of all?
Sir, as Rudnarayan said that we have to sort the array first, then we can put the array into a heap so that along with the processing time and the index in which it is coming in that array.
Okay.
Okay, so each time we can check the peak of the heap to get the minimum processing time, and so that we can get the minimum processing time in order of one time complexity. So then we can if and we can check the enqueue time of other indexes. If it is less, so we can add the processing time and add the index to the our answer array.
What is the enqueue time here?
Sir, as it is 3 2, so means at 3 time now the first process is coming which has a processing time of 2, no? So
Okay,
3 will be
so
your
if you put these elements in the heap, what will be picked first?
what, sir? Okay, so along with the processing time, so it will pick 1 first.
1, 2?
1 comma 2, yeah. No, sir. It will. We are putting processing time, no? So minimum processing time. So minimum is 4 comma 1.
But 4, 1 will not be picked, right? Because then you have to wait essentially 4 seconds. This is a
Yes,
much
sir.
more efficient solution.
Yeah. So instead of processing time, we can put the coming time, means when the process is coming, so that we can get 1 2 first. Then we will get 2 4 and 3 2 and 4 1.
But that is not the answer because at time 3, you had two options, 3 2 and 2 4. You will choose 3 2. The CPU will choose 3 2
Yeah.
because this has lower processing time.
Yes, sir.
Right. So can you modify your approach a bit to handle this scenario? Anyone? What modification can we do to what Shivashish mentioned? So what I'll suggest is have a timeline, something like this. So you have a timeline. So first of all, to maintain the indexes, right? To maintain the indexes and yet sort it, what I'll do is I create a job class. Easiest thing that I can do is I create a job class which has start time, which has processing time, and which has the index. Okay, and I create a job array. So I create a job array, jobs array. Okay, of job class, right? So once I've created a job array, now I can sort it based on the start times. So my indexes will still get preserved, right? So this was the one flaw in Rudnaran's answer, that the indexes got lost. We couldn't do anything because we have to return the indexes. So now when we sort the jobs array on the start time, so we are done, sorted. Now we start with the first element. Say we see car equal to 0. So we, okay, why the concept of using a heap? Because at any point of time, we need to find the best possible element, right? So for that, we will need to use some kind of a thing that always returns at that point what is the best possible thing, right? So it's a very greedy kind of an approach. And for doing that, here we will use a heap. Okay, because from multiple elements, if I have to choose one, I'll not be sorting it multiple times. So that was another flaw. We don't need to sort multiple times. We'll sort only once, right? So we can use a heap, but we'll not push all the elements in the heap, right? So we in the beginning we just push 1, 2. This in the heap, right? Because this is the only element at that time. So now when this is processed, what is the time? The time is 3, right? 1 plus 2. So we will push only those elements whose start time is less than or equal to 3. So in the sorted array, this element and this element qualifies. So these two elements are pushed in the heap, right? Then one of them is picked. Which one will be picked? This one will have to be picked based on our custom comparator that we will write, right? And when this element is done, what will be the current time? It will be 3 plus 2, 5, right? So within 5, what are all the things that are left with? So this can be pushed now. So now these two elements are there in the heap. Which one will be picked? This one will be picked, right? And finally, when this is done, when the time is 6, this one will be picked, right? So we'll process till the heap is empty. So this is how we can solve the problem. Okay, so we at any point of time when we try to figure out, okay, what is the best possible solution, we go for a heap based approach. Okay, so the next class will be talking primarily about heaps, right? We'll be solving multiple problems about heaps, and this is like a prelude to the next class. I don't have enough time today to continue, but the next class will be starting with this problem. Okay, so where we have to maintain an index and we have to figure out, okay, so what are the elements at that point of time? So we cannot push everything into the heap in the beginning, right? That's not a correct approach, because the CPU will not have all the elements at the heap at its helm in the beginning itself, right? So that is one consideration that was needed to be made, and that is what we do to solve the problem. Okay. So I will not take questions today. I also have some other engagement in the evening, so I have to leave. But yeah, so this is what I had for today. So any questions before we wrap quickly? You guys have any questions, concerns? Not even. Okay, I don't see any questions or hands raised, so I'll wrap today. Okay, so the next class happens in the next week, so we don't have class tomorrow. So enjoy your New Year parties and stuff. Have fun. Stay safe. The COVID things are on a rise again, right? And yeah, we'll meet in the next. We'll meet on next Friday, and we'll do heaps. Okay, I generally don't want to go like, for those who have been regular, you know that I don't talk about a data structure, but heap is such a data structure that needs prelude. I want all of you to know what are heaps, how they're implemented. I will not go into the basics of heaps, like I'll not be doing heapify and stuff like that, right? So we'll directly be looking at priority queue implementation in Java. So if you are using C++, or anything, look at the parallel implementations, how they work, right? and we'll be looking at heap-based problems on the next class, not the data structure. Right, so this is not a data structure course. This is more of a problem solving, how to develop the problem solving skills. Right, so we'll be directly solving problems which will need heaps in the next class, and yeah, we'll take it from there. Okay, so yeah, happy new year in advance to everyone. All the best, good parties, and yeah, bye bye.